Okay, it's time to get started. So we're pretty much ready, I think, to take the next exam. So we're going to go over one of the sample exams that I posted online up on Canvas. So today's notes I probably will not post because there's already a scanned version of this stuff already online. But it's good to see how it's developed. So first problem on that exam, this is exam 4AF. The instructions for the first two parts are: determine whether this series is absolutely convergent, conditionally convergent, or divergent. Now, our usual go-to test to check for absolute convergence is the ratio test. Occasionally the root test, and we would only not use those if the series we were testing was not going to work with one of those tests. In other words, if those tests give you the number 1 when you go find L, the tests fail, and then you have to go try some other test, like maybe a p-series test or a comparison test or something like that. But this one I think will work with the ratio test, so let's go ahead and dive right in with a ratio test. All right, so we're going to find L. L is going to be the limit as k goes to infinity of the absolute value of the k plus first term of the series. So we're going to replace each of these k's, and there are 3 instances, by a k plus 1. So we get -1 to the power of k plus 1 minus 1. And then we have k plus 1 squared instead of the k squared. And then down in the denominator, we've got 3 to the power of 2 times k plus 1 minus 1. All right, this k got replaced by k plus 1, so it's 2 times k plus 1, and then still with the minus 1 on the end. So there's the k plus first term of this series, now divided by the kth term. So that's just a recopy of what we have up here. -1 to k minus 1, k squared, divided by 3 to the 2k minus 1. By the way, notice that this is not a power series that we're working with. There are no x's in this, it's pure k's. Any one term of this series is a constant. So plug a 4 in for k, this would be a constant. Plug a 6 in for k, this would be a constant. This is not a p series. Coming later in the exam, but this is not one of them. All right, the absolute values. They won't have a huge effect on this because almost everything here is positive, but these two -1s will be 1 when you take their absolute value, right?
Hey, Alvin, did you buy a hotspot?
Let's turn Alvin here. Let's mute Alvin. There we go. All right. So now we're going to take the bottom fraction, flip it over, and multiply it by the top one, like that. Okay. So doing that, we get the limit as k goes to infinity of, all right, so k plus 1 squared, that's still there, over, now I'm going to simplify this as I rewrite it. So I've got 3 to the power of, if you multiply this exponent out, you'll get 2k plus 2 minus 1. Right? 2 times 1 is 2, minus 1 will be plus 1. Multiplied by, and then we flip this guy over, and we get 3 to the 2k minus 1 over k squared. Are there any questions at this point? No questions? Okay. All right, so now we can do a bit of reducing. So this 3 to the 2k minus 1 and the 3 to the 2k plus 1. How many more of them are there down here than there are up here?
There are 2.
Yeah, there's 2 more. You'd have to add 2 to 2k minus 1 to turn it into 2k plus 1. So if I do some canceling here, there's a couple of 3's left on the bottom, aren't there?
Yep.
3 squared down there. Unfortunately, the other guys don't cancel, right? There's no canceling available in the others, so we just have to deal with it. So now we have the limit as k goes to infinity. And I'm going to rearrange the order of writing these a little bit. I'm going to write the 1 over 3 squared first, and I'm going to put the two k terms, the ones that still contain k's, together in the same fraction like this. Okay. Now a couple of things. The 1 over 3 squared is a constant. Therefore, the limit has no effect on it, and we can take it out of the limit. The remaining terms, all we have to worry about with them, they're both polynomials, aren't they?
Yep.
And it's an infinite limit of a poly over a poly. All you have to look at are the lead terms. If you were to expand out the numerator, the lead term would end up being what?
K squared.
Yeah, k squared. And then on the bottom, we already have a k squared. And those two guys will cancel each other. And we'll have a 1. And 1/9 times the limit of 1. Limit of 1 is just 1. 1/9 times 1 is just 1/9. And there's our L. We found L. L is 1/9. Now remember, with the ratio test, we need to compare L with 1. This is definitely less than 1, which implies that it converges absolutely. Remember, when the ratio test works, it doesn't just guarantee convergence, it guarantees absolute convergence. This converges absolutely. Any questions about this one? Okay, let's do another one. So V, we have the sum as n goes from 1 to infinity of 2n plus 1 factorial divided by n factorial squared times 3 to the n. Okay, so factorials all over the place. The ratio test would probably be the way to go here. So let's apply it, the ratio test. Always tell us which test you're using, so that when we're grading it, we know what we're thinking, what your thought process was. All right, so can you see that in this case, even writing absolute values down at all is redundant? There's not a single source of negativity here, is there?
Nope.
Everything in sight's positive. So I'm going to skip leaving the absolute value bars on there at all. I'm going to leave them off immediately. And I'm just going to go straight for L to be the limit as n goes to infinity of the n plus first term over the nth term. All right, so the n plus first term, I'm going to replace the n here by n plus 1. So I get 2 n plus 1 plus 1 factorial divided by, and the same down here, I've got n plus 1 factorial squared times 3 to the n plus 1. So there's the n plus 1 version of everything. All right, over the original n version. So that's 2n plus 1 factorial over n factorial squared times 3 to the n. All right, and then we do the usual. We take this denominator, flip it, and multiply by the numerator. Now, as I rewrite this, I'm going to expand it out. So that will be the limit as n goes to infinity of, okay, expanding out this factorial in the numerator. 2 times n is 2n. 2 times 1 is 2, plus this other one is 3. So that's 2n plus 3 factorial. And then on the bottom, well, there's not much I can do to help that out, so I'll just write it straight up again. N plus 1 factorial squared times 3 to the n plus 1 times, and then this one flipped over, n factorial squared times 3 to the n divided by 2n plus 1 factorial, like that. Any questions so far? All right, now the factorials have an awful lot in common here. Let me get them kind of rearranged a little bit. I'm going to write these two factorials, this one and this one over the other. And I'm going to write these two factorials, which have the square on the outside, 1 over the other. And I'm going to write the 3 base exponentials, 1 over the other, just to kind of get things lined up so I can start thinking straight about what's going to happen here. So I've got the limit as n goes to infinity. Now the 2 that I underlined in red, as I rewrite this guy, I'm going to write it in its expanded form. I'm going to write it as 2n plus 3 times 2n plus 2. Remember, it keeps on going down by 1 times 2n plus 1. Now, from there on down, it will match this guy on the bottom, 2n plus 1 factorial. You okay with what I did there? This is the red stuff. This is these 2 red ones that I underlined in red. That's this guy here, and that guy there. These are the original 2 reds. Are you okay with that? Okay. All right, now the 2 that I underlined in green. Notice that both of the green guys have an outer square, don't they? So I'm going to write this next bit so that the whole thing has a square on the outside. Now up on top, I have n factorial. That's this n factorial with the square on the outside. On the bottom, I've got n plus 1 factorial. Now, how can I write that? I could write that as n plus 1 times n factorial. Okay, so these are the 2 green guys rewritten. All right, and then finally, I've got the 2 exponentials. I've got 3 to the n, and I've got 3 to the n plus 1. There's my 2 blue guys, like that. Now I'm ready to go canceling everything that I can. So these 2n plus 1 factorials, they cancel, right? This n factorial and this n factorial cancel. And this 3 to the n would knock this 3 to the n plus 1 down to just being 3 to the 1. All right? So gathering up the leftovers, we have limit as n goes to infinity of 2n plus 3, 2n plus 2, and then the bottom's gone there. Here, the numerator is gone, the denominator is still there. So on the bottom, I have n plus 1, but there's a square on the outside, remember. So there's an n plus 1 inside, squared on the outside, so it's n plus 1 squared. N plus 1 squared, and the numerator is just a 1. Remember, after you've canceled these, there's a 1 left behind. So 1 squared is still just 1, it doesn't matter. And then out of these guys, there's a 3 left behind, so times 3. We okay with that? Any questions? Okay. Now, if you were to expand these out, they're both polynomials. And so let's just jump straight to the conclusion. If that's a poly and that's a poly, and it's an infinite limit, all that matters is the lead terms. What will be the lead term of this numerator?
N squared.
4n squared, right? 2n times 2n is 4n squared. And some other terms that don't matter. And the denominator, what would be the lead term of this denominator if I were to expand it out?
Just n squared. Well, 1 over.
This guy.
3n squared?
3n squared, good. Yeah, 3n squared. Don't forget that 3 there. That would be part of it. 3 times everything that came from out of this. So the lead term would be 3n squared. And it's very important that you don't miss that, because if it would make a big difference to the answer if we miss something like that. All right, so these n squareds cancel. We're left with 4/3, which of course is a constant. And the final answer is that constant. And remember, this is why it's such a big deal that we don't miss things like the 3. What size is this compared with a 1?
It's
Greater than
greater
1?
It's greater than 1, yes. It's greater than 1, telling us what about the series?
Diverges.
Diverges. Now, say everything else was the same in the original problem, except instead of this being 3 to the n, it was 5 to the n. The bulk of the work would have been identical, but this would have been a 5 here. This would have been a 5 here. We'd have had 4/5, and our conclusion would have been what?
It absolutely
Yeah,
converges.
It absolutely converges, exactly. It would have made a difference between diverging and converging if that was a 5 instead of a 3, which is why it's so important that you don't lose little details like this 3 here. It could tip the balance from one form of answer to the other completely if you lose a little detail like this 3. Are there any questions on either of the problems we just did? All right, so moving on. Now we're going to start. Actually, no, we've still got 2 more problems of this kind. I was about to say we're going to start doing some power series, but I'm not. We have 2 more of the same kind of problem. So part C.
Mr. Barker,
Yes.
what's the difference between this convergence and absolute convergence?
Conditional convergence means that you only converge because the negative signs are there. And if you remove the negative signs, you diverge. An example would be the alternating harmonic series. Remember the alternating harmonic series? It goes 1 minus a half, plus a third, minus a fourth, plus a fifth, minus a sixth. That series converges, and you can prove it does with the alternating series test. But if you took the absolute value of all its terms, it turns into the harmonic series. 1 plus a half, plus a third, plus a fourth, plus a fifth. And that diverges. So the alternating harmonic series converges, but if you take its absolute value, it diverges. So we say that the alternating harmonic series converges conditionally. It has conditional convergence. If the minuses aren't there, it doesn't converge. So it does not converge absolutely. It only converges conditionally. That answer the question?
Thank you.
Okay.
Oh, thanks.
All right. So sum as k goes from 1 to infinity of e to the k squared divided by k factorial. This is actually a fairly easy one, I think. Probably easier than either of the ones we did already. There's no negatives here, so the absolute values in the ratio test will be a bit redundant. Let's skip the absolute values. And so we're going to find L. L is going to be the limit as k goes to infinity of the k plus first term of this series. So we put k plus 1s in where the k's are, and we get e to the power of k plus 1 squared over k plus 1 factorial divided by the original kth term, e to the k squared divided by k factorial. And I just got through saying I didn't need the absolute values, and guess what? I went and wrote them anyway. I apologize. But these are doing nothing, right? These absolute value bars. So I can just drop them. Let's take the bottom, flip it over, multiply by the top. Invert and multiply. So I get the limit as k goes to infinity of, and I'm going to rewrite this as I write it back down again. I'm going to rewrite the exponent in its expanded form. So this would be e to the k squared plus 2k plus 1. You okay with that? K plus 1 squared is k squared plus 2k plus 1. On the bottom, I'm going to expand this as well. Instead of writing it as k plus 1 factorial, I'm going to write it as k plus 1 times k factorial. And the reason for these rewrites is so that I can get my canceling going fairly smoothly when I flip this back over. This denominator factor here, it turns into this. And can you see how you can do some straight up canceling rather quickly here? Right, so the k factorial cancels the k factorial, leaving the k plus 1 behind. And the e to the k squared knocks out e to the k squared, but there's still e to the 2k plus 1 left behind. Right, subtract that power from that power. Okay, so now we have the limit as k goes to infinity of e to the 2k plus 1 over k plus 1. Now that limit is a L'Hopital rule type problem, isn't it? If you go to infinity, you get e to the infinity over infinity, which is infinity over infinity. That's where you'd like to use L'Hopital's rule. What's stopping us from using L'Hopital's rule right now?
K.
The fact that it's K.
The fact that it's k. K represents a discrete variable. It's only a 1 or a 2 or a 3 or a 4. It cannot be in between. Therefore, you can't take derivatives of expressions using k, because k doesn't represent a continuous variable. It's a discrete variable. So instead, we're going to trade this in now for an x version of the same limit. Because we have a theorem that says these two limits would have to be the same answer. We compared it to having beads along the wire. We say this is the bead version of the limit. If the beads lie on this wire, though, and the wire goes to a certain limit, the beads must be going to the same limit. All right, so we get this. And now we can use L'Hopital's rule on this. This is perfect for L'Hopital. So we apply L'Hopital, and we get the limit as x goes to infinity of the derivative of the top, which is 2e to the 2x plus 1, over the derivative of the bottom, which is 1. Okay? So derivative of this is the chain rule. That's where that 2 is coming from. It's the derivative of the power, and then the derivative of this is just 1. Now put infinity in again, and we get 2e to basically the infinity, so that's infinity. Now, the important thing about it is it bigger or less than 1? Yeah, quite a bit bigger, right? And so what does that tell us about the series?
Diverges.
Diverges. Right. That's it. Any questions about that one? Okay. D. What if we have the sum, as n goes from 1 to infinity, of 2e to the n minus 1 over 4e to the n plus 1, all raised to the power of 2n. Now, when I see this one, something catches my attention. The entire thing has a power of n attached to it. Actually, it's 2n, but the 2 isn't going to worry us very much. It has a power of n here. Now, the ratio test would work. I'm not saying you couldn't use the ratio test here, but there's a better test, a quicker test. If the power on the whole thing is an n, what would be a much better test to try using?
Root.
The root test.
Root test, because the root test takes the nth root of this, which will kill the nth power and make for an easier limit. So we don't use the root test very often, but it's nice to have in the toolbox because it's faster for problems like this to use the root test. So L is going to be the limit as n goes to infinity of the nth root of this. Now, it's supposed to have absolute values in it, but I'm not going to worry about the absolute values because they're not going to do anything. Not for these n values that we're using. Admittedly, there is a minus sign here, but if you start with n equal 1, 2 times e is like 5.4. 5.4 minus 1 is not negative. None of these terms are ever negative. Okay. Now, what is this nth root going to do to this 2n power?
Cancels the n.
Cancels the n part of it, though the square is left behind. Remember, you can think of the nth root as a 1 over n power, so you could think of the whole thing as the power of 1 over n. 1 over n times 2n is just going to be 2. So that gives us the limit as n goes to infinity of 2e to the n minus 1 over 4e to the n plus 1 squared. Okay. Now, we've got a limit on the outside that's going to infinity, and we've got this junk squared. Now we're going to take advantage of one of those limit theorems we learned back in Calc 1 that says limits of composite functions where the outer function is continuous. Now the outer function here is the square. X squared is very much a continuous function. If you have a composite function, outer, inner, outer is a square, inner is this ugly fraction, you're allowed to move the limit to the inside of the composition. So I'm going to move the limit to the interior there. And that gives me the whole thing in parentheses, limit as n goes to infinity of 2e to the n minus 1 over 4e to the n plus 1, all squared. Okay with this so far?
Yep.
All right, now there's various ways you can do this. This is going to infinity over infinity, so it's essentially a L'Hopital rule scenario. Again, because they're n's, not x's, I'd need to trade these for x's before I take L'Hopital's rule. But there is an alternative way to do this, and so I'm not discounting L'Hopital. You could certainly use L'Hopital here. There's nothing wrong with using L'Hopital here at all. But just to illustrate a different approach, what you could do is you could use a trick that your book has shown you in the past, and that's multiply top and bottom of the fraction by a quantity that would kill the biggest powers. In this case, the biggest power is e to the n. So I could multiply top and bottom by 1 over e to the n. Okay, the whole thing is still squared. Now what that does is it drives any appearance of n into the denominators of various terms. So we have the limit as n goes to infinity of, don't forget you're distributing this onto both terms. In the top, we're distributing it onto both terms on the bottom. And we get 2, because 2e to the n times 1 over e n just cancels to 2, minus 1 over e to the n. And on the bottom, we get 4 plus 1 over e to the n, all squared. Now, what was the advantage to doing that? Why is it now easier to tell what's going on? Well, if you send n to infinity, what's e to the n going to do? It's going to go to infinity. And what's 1 over infinity going to go to?
0.
Yep. And the same comment on the bottom. This 2 is going to go to 0. All right. As n goes to infinity, it will drive these two towards 0. That was the reason for doing this multiply top and bottom by 1 over e to the n, because it makes every appearance of n be in a denominator. And if n goes to the infinity in the denominator of an expression, that term is going to head for 0. So that's a way of getting through this without even using L'Hopital's rule. All we have left is 2/4 all squared, because the limit's been taken now. 2/4 of course is 1/2 all squared, and 1/2 squared is 1/4. And 1/4, again, root test, just like ratio test, you have to compare it with a 1. 1/4 is less than 1, which implies what?
Absolute convergence.
Yes. You have absolute convergence. All right. Any questions about that one? Now, if you don't like this trick, again, what could you have done instead? Traded the n's for x's and used L'Hopital's rule. You'd end up in the same place in the end. The derivative of the top is 2e to the n. The derivative of the bottom is 4e, actually 2e to the x, 4e to the x. The e to the x is canceled. The 2 and the 4 reduced to 1/2. You square it, you still end up with 1/4. Same answer. Any questions about that one? Okay. Problem 2. I want you to find the Taylor series of f of x equals the sine of 3x centered at A equals pi over 18. All right, so in order to get this Taylor series, we're going to have to start cranking that.
Professor, we can't see. Oh, there we go.
Sorry about that. So that's the function. We need it and its derivatives, and we need to evaluate them all at pi over 18. So the original function is sine of 3x. Its first derivative is 3 cosine of 3x. Its second derivative would be negative 9 sine of 3x. Its third derivative would be negative 27 cosine of 3x. Every time I apply the derivative, don't forget the chain rule is going to bring another 3 out, right? The derivative of 3. Derivative of 3x is 3. Derivative of 3x is another 3, so that goes with the first 3 and gives you a 9, etc. It's going to keep on getting multiplied by 3 each time. All right, maybe we have enough terms. They said find the first 4 non-zero terms. Let's hope that this is 4 terms. Let's hope that they're all non-zero. So now I'm going to start plugging in the center and see what it produces. All right, so what is f of pi over 18? Let's go into the sine of 3 times pi over 18. But that is the sine of pi over 6, isn't it, if you reduce it? And that's 1/2. We know that from memory. Okay, what's f prime at pi over 18? Well, that's 3 times the cosine of 3 times pi over 18, which is the 3 times the cosine of pi over 6, which is 3 times the square root of 3 over 2. Again, from memory, we know that. All right, f double prime at pi over 18 is negative 9 times the sine of 3 times pi over 18, which is negative 9 times the sine of pi over 6, which is negative 9 times 1/2, which is negative 9/2. Okay, and one more, f triple prime at pi over 18 is negative 27 times the cosine of 3 times pi over 18, negative 27 times the cosine of pi over 6, which is negative 27 times the square root of 3 over 2. All right, so we got those. Those didn't go too badly. At least they were all values we had from memory, either the sine or the cosine of pi over 6 in each case. All right, so now we write out the answer. Now remember, the generic formula for the Taylor series is f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed. 1, 2, 3, 4 terms, that's all they asked for, etc. And we just figured these out. We know f of a for us, f of pi over 18 is 1/2. F prime of a is 3 root 3 over 2. F double prime of a is negative 9/2. F triple prime of a is negative 27 root 3 over 2. Okay. Meanwhile, what are these a's here going to be replaced by?
Pi over 18.
Exactly, pi over 18, the center. A represents the center. So if you just plug those in, we're done. So we have 1/2 plus 3 root 3 over 2 times x minus pi over 18 minus 9/2 times x minus pi over 18 squared minus 27 root 3. Oh, I lost something here.
You lost the factorial.
I lost the factorial. It's 2 times 2 factorial there. And here, it's 2 times 3 factorial here. That 2 times the 3 factorial times x minus pi over 18 cubed plus and so on. So now I'm going to simplify these. So I've got 1/2 plus 3 root 3 over 2 times x minus pi over 18 minus 9 over 2 factorial is just 2 times this 2 is 4 x minus pi over 18 squared minus 27. Actually, I can do some reducing here. 2 times 6 is 12, but 27 and 12 have a common factor in them, don't they?
Yes.
They both have a 3 in them. So I could reduce that. 3 and 3. 3 goes into this 9 times. 3 goes into this 4 times. So that's basically the final answer. I'm not going to write it out again, but you get the idea. That's it. There's our Taylor series, 4 terms of the Taylor series of the sine of 3x, centered at pi over 18. Any questions about that one? Okay. Now what most people would say is the hardest problem on the test, problem 3. I mean, we did a bunch of these already, so I don't think you'll find it too hard. They want the interval and the radius of convergence of this power series. And the power series is the sum, n goes from 1 to infinity, of -1 to the n minus 1 times x minus 4 to the n over 3 to the n times the square root of n. All right, find the interval and radius of convergence of that series. And we do it using the ratio test, or potentially the root test, but usually the ratio test. When would I use the root test again? If everything had a power of n. Now, it was looking pretty good here and here, but it's the square root that messes that up, isn't it?
Yep.
If that square root wasn't there, I definitely use the root test, because everybody would have a power of n. All right, so L equals the limit as n goes to infinity of the absolute value of the n plus first term, which is -1 to the n, x minus 4 to the n plus 1, over 3 to the n plus 1, square root of n plus 1, over the nth term, -1 to the n minus 1, x minus 4 to the n, over 3 to the n, square root of n. Okay, now these negative ones are killed by the absolute value. And the absolute values won't affect the exponentials base 3. The absolute values won't affect the square roots, but the absolute values will affect x minus 4 depending on the value of x. For example, if x was 0, 0 minus 4, right, is negative. If x were 5, it would be positive. If x were 2, it would be negative. So it depends on what x is. So these absolute values do need to be retained, that they only need to be retained for the x minus 4 factors here and here. They don't need to be applied to this other stuff because that's always positive. So I am going to flip the bottom over as usual, and I'm going to tuck in those absolutes to only apply to the x minus 4s, and I'll leave it off everybody else. All right, so doing that, I get the limit as n goes to infinity of the absolute value of x minus 4 to the n plus 1 over 3 to the n plus 1 square root of n plus 1 times, and remember the other one's going to go upside down, 3 to the n square root of n over the absolute value of x minus 4 to the n. Now before we take the limit, we cancel as much as we can. 3 to the n cancels 3 to the n. There'd be a solitary 3 left here. X minus 4 to the n cancels x minus 4 to the n, but there'd be one of these left. X minus 4 to the 1 would be left behind. So collecting up the leftovers, we have the limit as n goes to infinity of the absolute value of x minus 4 over 3. These are the two components that don't involve n, times, and then we have the root of n over the root of n plus 1. I'm going to write that as one big root. That's the same thing, isn't it? Root of n over root n plus 1, root of n over... This and this are equivalent. Root n over root n plus 1 is the same as big root n over n plus 1. Now, since these guys in the first fraction don't involve n, what am I allowed to do with this whole thing?
Remove it.
Yeah.
Yeah, exactly. I can put it in front because it's a constant as far as that limit is concerned. Only this stuff involves n. And meanwhile, I have one of those composite function things going on again. I have an outer function, which is a square root, and I have an inner function, which is this fraction. What did we say you could do with limits on the outside of composite functions?
Bring them into the root.
Exactly. We can move it inside to the root. So I'm going to do that. I'm going to move it onto the inside. So two things at once there. And I have the absolute value of x minus 4 over 3 times the square, whoops, I lost my limits. No, I didn't, hang on. The limit's going to the inside. I didn't lose my limit. Times the limit is n goes to infinity of n over n plus 1. Yeah. Okay, now what we have now for the limit is a poly over a poly. So as usual, infinite limit of a poly over a poly, the only thing that matters are the lead terms. So on that basis, we've got n over n. Absolute x minus 4 over 3 times the square root of the limit as n goes to infinity of n over n. Now, of course, that just reduces to a 1, doesn't it? And the square root of 1 is 1. So the absolute value of x minus 4 over 3 times 1, which is itself. Now, this is a ratio test. We're looking for the interval of convergence, right? Interval of convergence. What does this need to be to get convergence?
Less than
Less than
1.
one.
Yes, it needs to be less than 1. Now we're going to apply, and I know I keep repeating this because I know this is a rule that students often forget. If the absolute value of A is less than B, that implies that A must lie between
Negative b and positive b.
negative B and positive B. Now that fact is going to be used as we try to create our interval of convergence. We have this is less than 1, right? So using this rule, what does this quantity without the absolute value have to be? Between negative 1 and positive 1? Okay, using this rule. Actually, what we might want to do is get rid of the 3 first. I could multiply both sides by 3. So if we multiply through by 3 here on both sides, you get the absolute value of x minus 4 is less than 3. Is that right?
Yep.
And so that implies that x minus 4 itself would lie between, using this rule, where does it lie between?
7 and 1.
Oh, that's your final answer. This
Negative 3
quantity,
and 3.
yeah, that lies between negative 3 and 3, yeah. So then we add 4 to everything to get x isolated, and we get that 1 is less than x is less than 7. So that's the heart of our interval of convergence. It's not the entire interval because we may have to include the endpoints, but that's the heart of the interval of convergence. All right, so now the only thing remaining to verify is what about those two endpoints?
Whether or not they converge or diverge.
Yeah, we have to tell whether they converge or diverge. We don't know for sure. The ratio test cannot tell us that. They need to be checked individually. They are the values for which this limit here would have been 1. For example, if you put 7 in here, 7 minus 4 is 3. Absolute value of 3 is 3. 3 divided by 3 is 1. And what does the ratio test tell you if you get 1? It tells you nothing. And if you put 1 in here for x, 1 minus 4 is negative 3. Negative 3 absolute value is 3. 3 divided by 3 is 1. Same deal. The test tells you nothing. The endpoints of your interval convergence always correspond to a failure of the ratio test. They correspond to the ratio test being 1. All right, so endpoints. We need to do individual tests for those. All right, so let's test 1 first. X equal 1. Now remember, for this, you go back to the original function, the original power series here, and you plug in that endpoint, 1, where the x is. And so it becomes the sum as n goes from 1 to infinity of negative 1 to the n minus 1 times 1 minus 4 to the n over 3 to the n square root of n. Okay. Now, 1 minus 4 is negative 3. So we get the sum. N goes from 1 to infinity. Negative 1 to the n minus 1 times negative 3 to the n over 3 to the n square root of n. Now these guys, you could merge them into the same fraction. Let me rearrange the order I'm writing everything. They both have the same power. I'm going to write this as negative 1 to the n minus 1 over the square root of n times negative 3 over 3, both to the n. You okay with my rearranging there?
Yep.
Okay. Now it's written that way, though, I can reduce the inside of this down to negative 1. So I have the sum from 1 to infinity of negative 1 to the n minus 1 times negative 1 to the n over the square root of n. Notice how these now have the same base, negative 1 in both cases, so you add the powers together. And you get n equals 1 to infinity of negative 1 to the, add the powers, 2n minus 1 over the square root of n. You okay with this? All right, now observation here. What sort of quantity is always 2n minus 1? What kind of quantity can you guarantee it is?
Positive.
I think that's true. You're right. It's odd. It's guaranteed odd, isn't it? Because 2n is even, and an even minus 1 is bound to be an odd. So you're raising negative 1 to an odd. What can you guarantee you will always get if you raise negative 1 to an odd power?
It'll be negative.
Yeah, it'll always be negative 1. Okay, permanently negative 1, not alternating. Not alternating, it just is negative 1, period. So this is becoming sum from 1 to infinity of negative 1 over the square root of n. Now that negative sign is like a negative constant. It's allowed to move that outside, just like you can move any constant outside. And the reason I'm doing that is to make an emphasis here of what we have left. We have 1 over n to the 1/2 power, don't we? Square root of n. Now what is this?
A power series.
No.
Sorry, not a power series, a P series.
P series.
That's the p series with a p-value of 1/2. What do those always do?
Diverge.
Diverge if the p-value is less than 1, right? Less than or equal to 1. So this is a p series with p equal to 1/2, which is less than or equal to 1. So it diverges. So that endpoint, 1, is not going to be included in the final interval of convergence. That endpoint diverges. Now we have the other, are there any questions on this before I move on to the next endpoint? All right, so the other endpoint, x equals 7, we do the same thing. We plug it into the original series back here. And that's the original series. So I'm going to be putting a 7 in where that says x. So this will become 7 minus 4 to the n. So you won't be able to see them both on the screen at the same time, unfortunately. So I get the sum, as n goes from 1 to infinity, of negative 1 to the n minus 1 times 7 minus 4 to the n over 3 to the n square root of n. I want to verify, maybe I should put them side by side here. Can you see them both then? There's the original series. Here is it with a 7 plugged in. Can everybody see that? The x has been replaced by 7. Everything else is the same. Okay, and now I simplify. So obviously 7 minus 4 is 3. So this becomes the sum. N goes from 1 to infinity. Negative 1 to the n minus 1 times 3 to the n over 3 to the n square root of n. And the 3 to the n's completely cancel, leaving me with the sum, n goes from 1 to infinity, of negative 1 to the n minus 1 over the square root of n. Now you can rewrite that as the sum from 1 to infinity of negative 1 to the n minus 1 over n to the 1/2 power. So what is this?
A p-series.
It is a p-series, but what can you say about the sign?
Alternating.
It's an alternating p-series. This is an alternating p-series. Now, the conditions for convergence for an alternating p-series are a little bit more forgiving. This is an alternating p-series with p equal to 1/2, but p equal to 1/2, all you have to have your p-value be is bigger than 0 to get convergence if it alternates. And it is greater than 0, so it converges. Okay, so let me just make a note here for reference. P-series converge if P is bigger than 1. Alternating P-series converge if what?
If p is greater than 0.
Yes, if P is greater than 0. All right. That is easily proven, by the way, by just applying the alternating series test to any p-series with p greater than 0. The alternating series test will quickly establish that an alternating p-series will converge. The AST will prove it. And I don't need you to prove it on each problem. If you get an alternating p-series on your exam, feel free to just say, okay, p is bigger than 0. The p is not negative, it's positive. Therefore, it's going to converge. You don't need to go through a full AST to prove that. All right, final answer to this question. What's the interval of convergence? Remember it was from 1 to 7? What have we just concluded about 1?
It
It's not
diverges.
included.
Diverged, and about 7?
Converges.
Converges, so I have to include it. So I can write it that way. Or you could use interval notation instead if you want. You could write it this way, with a parenthesis in the bracket. And it also asks for the radius of convergence. Now that the radius of convergence is the distance from the center out to the edges. What was the center of this series? Here's the original format. The center was what?
4.
4. Well, how far is it from 4 up till 7?
3.
3. Or from 4 down to 1?
3.
3. So 3 is the radius of convergence here. Any questions about that? Well, obviously we're out of time for today. Remember, you do have this exam coming up. Remind me again, Monday is what you voted for, wasn't it?
Yes.
So you have this exam coming up on Monday. We will easily finish going over the sample. In fact, the remaining problems are quite easy, quite trivial, in fact. We'll bang those out in probably 15 minutes. And so this exam is coming up on Monday. And we'll finish the sample exam on Friday, and I will start on the next chapter also on Friday, the final chapter. Remember, there will not be an exam over the final chapter that's separate. We won't have time for that. We're going to merge those questions onto the final exam itself. There won't be a separate chapter 10 exam. Question, yes, Angie.
On the exam, will we be given a function and we have to write out the Taylor series?
Yes, absolutely, you will be. Just like you were here. Just like that problem right there. Find the Taylor series of, get it down here far enough. Just like this one, there'll be one like that, for sure.
Do we have to write it out in summation form?
No, I only asked you for a first, usually I ask for 4 terms, sometimes I ask for 5 or 6. But I'll ask you just to write out the first few terms, just like we did here, right? You wrote out the first few terms and that was the answer.